Greetings to all of you. Prior to our lecture 3, which is part 2 of SFs and BMs movement, I want to give this brief introduction to computation of support reactions. Obviously, in this particular topic, it's very important to understand various types of supports that are used to attach structures to the ground, and also how to sketch their free body diagrams. And that was essentially covered in lecture 1, and where we also saw real-time application, or where we can find these kind of supports in real-time structures. Now, in lecture 2, which is SFs and BMs movement, which is basically the start, we basically learned about different kinds of beams, and then how to convert distributed loads to equivalent concentrated loads, and so forth. Now in lecture 3, essentially, we are progressing, and the next step, which is very important, is computation of reactions. But it's very important to understand how we go around it, So if you are doing computation of reactions, the basic step to follow is you conceptualize the problem, which means you need to, first of all, look at the problem, understand the problem, devise strategy of how to solve the problem mentally, right? So you don't only start working, you first have to understand the problem mentally. Then you need to draw free body diagram of the structure. Free body diagram means you are representing the various supports by the appropriate reactions. Okay. And then the step 3, you check for static determinacy. This step 3, we did that in lecture 1, where we learn how to calculate degree of static determinacy of structures. And then the step 4, after you have done that classification, you can now determine the unknown reaction. And then finally, you have to check your computations. Now, basically, prior to this particular issue, one main thing, which is basically the focus of this short video, is to explain to you what is called sign convention. Sign convention is a language. So it's a language that wherever we see such signs in strength of materials, everybody understands what they mean, and we use that to communicate, and very important when we are doing analysis. Now, so before you be able to compute reactions, this important sign convention must be well understood. Okay? Right. So, the first thing here that you need to understand is the kind of forces we have. Okay? Now, if you look at the forces we have, first of all, we have a vertical force. Okay? So if you have a vertical force like this one, if it is, remember, force is a vector quantity, so it has magnitude and direction. So you have a line with the arrow. So if the force, vertical force is showing upward, right? If it's showing upward, it means positive. And if it is showing downward, negative. So it means wherever you see an upward force, the sign you use is positive, and wherever you see a downward force, the sign is negative. And the unit is basically Newton or kilonewton. Now, anytime we write F subscript Y, we are referring to vertical forces. Basically, in the normal Cartesian, we say in the Y direction. Right? Then we have horizontal force. So we represent that with capital F subscript X. So any horizontal force moving to the right is positive and to the left is negative. And the unit of the force can be Newton or kilonewton. And then finally, we have what we call moment or couple, represented by capital M. Now, moment is considered as clockwise if the rotation is in the order of how our clock moves. You know, our clocks actually, the way it moves, in that kind of movement, we call it clockwise. Is that right? And then anything counter or opposite to that movement is called anti-clockwise. Okay, so you see this one. Okay, so this is basically a clockwise moment. You see how the rotation is going like this. Okay, so if it is anti-clockwise, we'll consider that to be positive. And if it is clockwise moment, we'll consider that to be negative. Is that okay? So these are the basic sign convention we need in the analysis of support reactions. So take note, these sign conventions, you have to be consistent. If you decide that clockwise moment is positive, then anti-clockwise must be negative. And you have to maintain the same sign convention throughout your analysis. You don't get to a certain point, you say anti-clockwise is positive, then the next moment you say anti-clockwise is negative. No. All right. So I'm adopting the right hand rule. So I'll consider anti-clockwise to be positive and clockwise to be negative. The next thing I want to show you is how do you know? Okay. How do you know whether it is clockwise, anti-clockwise, and so forth? How do you know? How do you know? So here, I want to use this to explain how do you now determine whether the thing is clockwise or anti-clockwise. So let's see how this can be done. Right. Okay. So let me use this. Right. So let me just draw a beam here like this. And then let me draw a hinge support here. And then a roller support here. Okay. So let me put a force here. Let me put another force here. Let me put another force here. So P1, P2, P3. Okay? Well, let's take it like this. And then let's consider these distances. Okay? So let me say that this is 2 meters, 3 meters, 4 meters, 5 meters. So if you want to analyze this, as we already know, basically you need to draw your free body. Is that okay? So free body, this one is vertical and horizontal because it's a hinge. This is roller. So basically, this beam will be numbered as salient points. So you say A, B, C, D, and E. So watch how I'm going to number the reactions, okay? So if the reactions are at point A, vertical reaction, I'll call it capital V and then subscript A to show that vertical reaction at point A. Then the horizontal reaction will be capital H subscript A. You get it? And here we have a reaction at E. So I'll say capital V subscript E. So this is a basic nomenclature for reactions. Now, if you want to do this calculate reactions, you first need to be able to decide on what we call pivot. Okay? So if you pick the pivot, okay, if you pick the pivot, you can't establish two pivots at the same time. You can only establish one at a time. So if you want to determine clockwise moment or anti-clockwise moment, you need to use pivot. First, establish a pivot. And I will admonish you that, yes, the pivot can be established anywhere. But to simplify the analysis, consider the supports as your pivot. If you do that, your analysis will be simplified for you. Is that okay? So here, if I want to take moment at A, then it means I have to establish a pivot at A. So let me take this as too big. Let me make this my pivot, okay? Let me make this. So now I'll draw a big triangle here to signify that this is my pivot. Now, how do I know these forces are clockwise and anti-clockwise? Very simple. You must always relate it to the pivot. So if you look at the force P1, you consider this as you how to draw a circle with a compass. Is that right? So you always make sure the pinpoint of the compass is always at a pivot. So if I'm considering force 1, the pinpoint of the compass here, you open the compass to the P1 force and then draw a circle by following the arrow of the force, right? So this one will be like this. Do you see? So this what? So if I'm to go like this, that will be what? Clockwise moment. Again, if I am at the pivot open to P2, trying to move in the direction of the force, that will be clockwise moment. Is that right? So at the pivot again, I move my compass to P3, try to draw a circle, and that will be clockwise moment again. Okay? Look at the force here, VE, right? That VE force is showing up. So I'm going to follow the direction. So my pivot at A, open my compass, follow the direction of the arrow is going to go like this. That'll be anti-clockwise moment. Is that okay? Everybody here should remember that force, in other words, let me say, moment is equal to force times perpendicular distance. You must remember this all the time. Moment is force times perpendicular distance. So now we have established this is clockwise moment, the P1. How do I calculate the distance? The distance is always calculated to the pivot. So the pivot becomes a reference point. All distances must be calculated to the pivot. Okay, so if I take the P1 force, though I know it's clockwise moment, the distance will be from here to the pivot. Is that okay? That will be 2 meters. Now, if I go to the P2, relative to my pivot at A, the distance will be from here all the way to P2. So what do? I add 2 plus 3, and this will be 5. This will be 2 meters, 5 meters. If I look at the P3, then it's from here all the way toward point D. And if I add everything together, what do I get? I get 9 meters. And if I look at the VE force, then I have to calculate the distance from the VE force all the way to the pivot, right? So remember that all the time you must calculate from the force in question to the pivot all the time, right? So in this case, adding all this together, I'm going to get 14 millimeters, 14 meters. Is that okay? Very simple. Now, if you move the pivot, then the moment will also begin to change. Okay? So this is we used point A as a pivot. So let's see what happens. Let's see what happens. If now we decide to use some, as I indicated earlier, you cannot have two pivots established for the same. Once you move the pivot, okay, if you want to establish another pivot, the existing one no more exists. So, like I said, it's advisable to take pivot at reactional at supports. Okay, so here I'm establishing a new pivot here. Is that okay? So let's say this is another pivot. So this means you are taking moment at E. You are taking moment at E, which means E is now your pivot. So if you now take your compass pinpoint here, open to force P3, follow the arrow. You see the arrow is following down. Follow the arrow as if you are drawing an arc, and this will be your anti-clockwise moment. The same point again, I open to P2 like this. You see? And this anti-clockwise moment. The same thing here, I open to P1 again. There is also anti-clockwise moment. If you look at the VA, if I follow the force with my pin here at E, it's going to go something like this. Is that right? So that's clockwise moment. Is that okay? Well, if you look at the horizontal force, it's going to be along the beam. So the distance will be 0. So let's forget about that for now. So if I look at the force P3, the distance is always to the pivot, right? So I have to calculate from here to the pivot. And this will give me 5 meters, isn't it? If I look at the P2, I must calculate from P2 all the way to the pivot again. So that will be 4 plus 5. That will be 9 meters. If I look at P1, I calculate from P1 all the way to the pivot again, and I get 3 plus 4 plus 5, making 12 meters. And then VA, I calculate from the VA all the way to this place, right? So it's just a simple analogy, like you are drawing a circle, but make sure you follow the direction of the arrow, right? So supposing there is a force here like this, let me call this P4, and my pivot is at point E. If I'm to follow the direction of this arrow, then this force is clockwise moment. You get it? Very, very simple. And always remember that the moment is force times distance, not distance times force. Okay. I believe that with these little illustrations, you are able to understand how to determine whether this is clockwise moment or this is anti-clockwise moment. So remember, in this particular class, anti-clockwise moment is considered positive, clockwise is negative, upward force is positive, downward is negative, and then horizontal force to the right is positive and to the left is negative. So essentially, it's just like the normal Cartesian plane. Do you remember? This is X, this is Y, and remember this is plus, this is also plus, and this side is negative Y, isn't it? And this is negative X. So it's the same thing. If the force is moving up, it's positive. Moving down, it's negative. Moving to the right is positive, and then moving to the left is what? Negative. That's all. And then the moment with this, you see the arrow, that's what? Anti-clockwise, isn't it? and this is positive per sign convention. And this one is clockwise, so negative. So anywhere you do clockwise movement, you put negative, anti-clockwise, you put positive. So the last thing here is that in computation of reactions, we are going to deal with determinate beams. So we use this one, sum of forces in the y direction is equal to 0. Sum of forces in the x is equal to 0. And then sum of moment about a point is 0. So these are the equilibrium equations that we are going to use to calculate. You remember, we will be dealing with determinant problems. So if I'm calculating the reactions, I'll use this last equation, the sum of moment, to calculate reactions. Anytime I have a horizontal force, I'll use sum of force in the x direction. And anytime I have a vertical force. So where it's very important to know, after your calculation, you should be able to check whether your calculation is correct or not. And that is where this one becomes very handy. Use that one to check. If you check and your answer is 0, it means your calculation is correct. If your answer is not 0 and is positive or negative, it means your beam is in motion. Your beam is no more a static beam, but is a dynamic beam. And certainly, if you construct such structures on site, because the beam will be trying to force its way out, right? It means that there will be a lot of cracks. And if the columns are not strong, the columns may collapse before it gets to the site the next day. So doing the right analysis is very crucial, and make sure your analysis is checked. So I think that I've been able to help to be able to determine how to know whether the moment is clockwise, how to know it's anti-clockwise, and so forth. This is the first step in determining or in the approach of calculating support reactions. So this one will bring us to the end of today's short tutorial session. All right? So I wish you the best, and you can give me, if you require any further support, you just give me, let me have your comments in the comment section, and I will review your comment and also support you. Right? All the best.